working on problem number 3, and we're being asked to use the limit comparison test to show that this series is convergent, right? So the key here is convergent, which means I want to compare it with another series that is convergent. And limit comparison test that if I do the limit as n goes infinity of an over bn, and this limit exists, right? Call it L. And let's say, if an converges, then so does bn, right? There's some conditions such as they both have to be positive in order for this to be true, right? So, and this will always be positive for n greater than 1. So we want to think, okay, what am I going to compare this to? Well, let's compare it to a series we know converges, such as 1 over n squared, right? So let's start with this. This one converges because it's a p series. P equals 2, which is greater than 1, right? Therefore, this converges. So then we're going to use limit comparison test, right? We're going to do limit as n goes to infinity of 1 over n squared over 1 over n squared plus 1. And this is going to turn into, it's the same as multiplying by the reciprocal, right? So it's going to be n squared plus 1 over n squared. And this limit equals 1, right? So since this converges, therefore, and we already showed this, right? Therefore, this series also converges, right? We probably could use direct comparison test instead of limit, but yeah, right? So if it just says comparison test, then that would be like direct comparison test, but it wanted limit comparison test. Next is, so let the sum of some series equal this. We want to figure out what the interval of convergence is. And anytime you're asking for an interval of convergence, this is going to be a ratio test, right? So remember what ratio test says. Ratio test says limit as n goes infinity of absolute value of an plus 1 over an. It converges if this is less than 1, diverges if this is greater than 1, and if it equals 1, it fails, right? So let's go ahead and set this up. We're going to write limit as n goes to infinity, absolute value, x minus 3 to the n plus 1 over n plus 1 squared plus 2. Instead of dividing, I'm going to multiply by the reciprocal, which is n squared plus 2 over x minus 3 to the n. Right, this is where we need to do some algebra to work this out. On the top, don't lose your absolute value brackets yet. This is going to be x minus 3 times x minus 3 to the n. And then over here is n squared plus 2. On the bottom we have, let me go and multiply this out, n squared plus 2n plus 1, which then will be plus 3, times x minus 3 to the n. We're trying to show convergence, so we're going to try to show this is less than 1. These two will cancel. At the same time, the n doesn't affect the x, so I'm going to pull that x out. I'm going to write it here. And then limit n goes to infinity of n squared plus 2 over n squared plus 2n plus 3. And we're trying to show we can get rid of the absolute values in here because this will always be positive. We're trying to show this is less than 1. So we evaluate this limit. This limit is equal to 1, right? So it's like x minus 3 times 1 is less than 1. Okay, this is what we call our radius of convergence, but it's not our interval of convergence. To start our interval of convergence, let's go ahead and set up this inequality, such as like this, right? That's basically what the absolute value means. What we need to do is we need to test the endpoints, right? I need to test these, right? So let's start with if x equals -1. Oh no, sorry. We're not quite there yet. We haven't solved it yet. We need to go ahead and add this 3. So this is 2 is less than x is less than 4. So I need to test 2 and 4. So if x equals 2, this series turns into, right, we're just putting a 2 here. 2 minus 1 is -1. So we have absolute value n equals 1 to infinity of negative 1 to the n over n squared plus 1. Right? We can test for absolute convergence, right? So we can test, well, let's see. Yeah, let's do alternating series test. Alternating series test. First, we want to show that the limit as n goes to infinity of 1 over n squared plus 1 goes to 0. Does it? Yes. And next, we need to show that an plus 1 is less than an. So we're trying to show that 1 over n plus 1 squared is less than 1 over n squared plus 1. If we work this out, we'll have 1 over n squared plus 2n plus 3 is less than 1 over n squared plus 1. We could actually write out a multiply across here. We get n squared plus 1. We're trying to show that n squared plus 1 is less than n squared plus 2n plus 3. Right? Subtract these, and I think you can show that this is true when n is, for all n values greater than 1, right? So you get in there. Like this has to be true if n is greater than 1, right? Plug in 1, 2, 3, this will always be true. So, therefore, by alternating series test, well, I've shown these two things. We've showed this as well. By alternating series test, that sequence converges. Right? So that means we can put an or equal to bar here. We also already showed that if I plug in 4, right, go back up here to my original. If I plug in 4 here, this is going to be a 1. 4 minus 3 is 1. 1 to the n, which is just 1. It actually turns into this series. And so that one also converges. I already did that work, so we put an or equal to bar there as well. And that should be it, because we already, because we already showed that one. So you can just say C problem 3 for that one. You shouldn't have to redo all that work. Okay, that's it for problem. So you say C problem A.